Tonight on The Sleepy Scientist, we're drifting gently through the vast cosmic ocean, where the James Webb Space Telescope has opened windows to realms so distant and ancient that they challenge everything we thought we knew about our universe. In the quiet space of deep contemplation, we'll explore discoveries that have fundamentally shifted our understanding of cosmic evolution, galaxy formation, and the very nature of space and time itself, like whispers in the night. These revelations come to us across billions of years, carrying messages from when the universe was but a child, barely recognizable compared to the mature cosmos we observe today. Gently, we discover that our most sophisticated space observatory has peered so deeply into the cosmic past that it has found a universe far more complex, mature, and surprising than our models ever predicted. In the peaceful darkness of space, where light takes eons to reach us, James Webb has been our quiet sentinel, collecting photons that began their journey when the first stars were igniting, when the first galaxies were taking shape, when the fundamental structures of our cosmos were still forming in the gentle embrace of cosmic time. Tonight we'll float together through these extraordinary discoveries, examining how this remarkable telescope has revealed mature galaxies existing far earlier than theory suggested possible, supermassive black holes that formed with impossible speed, and cosmic phenomena that whisper of processes we're only beginning to understand. As our journey continues through these revelations, we'll maintain our gentle pace, allowing each discovery to settle peacefully into our consciousness, like starlight settling into the quiet pools of space. The James Webb Space Telescope represents humanity's most ambitious attempt to peer into the cosmic deep, equipped with instruments so sensitive they can detect the warmth of a bumblebee on the moon. In the quiet space of its observations, this technological marvel has been silently revolutionizing our understanding of the universe, one photon at a time, one discovery at a time, with the patience of cosmic time itself. As we begin our peaceful exploration tonight, imagine yourself floating in the serene darkness of space, surrounded by the gentle glow of distant galaxies, each one a testament to the universe's capacity for beauty and complexity. Let's drift into this cosmic meditation together, where science and wonder merge in the quiet contemplation of existence itself. The story we're about to explore unfolds like a gentle revelation, where each discovery builds upon the last, creating a tapestry of understanding that grows more intricate and beautiful with each observation. In the vast cosmic ocean where we find ourselves tonight, the James Webb Space Telescope serves as our guide, leading us through discoveries that are reshaping our fundamental understanding of cosmic evolution. Now we float toward our first gentle revelation, understanding that the journey we're embarking upon will take us through realms of space and time, where the impossible becomes routine, where the shocking becomes contemplative, and where the mysteries of the deep universe unfold with the quiet majesty of cosmic dawn. In the quiet space of human ambition and scientific curiosity, the James Webb Space Telescope was conceived as a gentle successor to the beloved Hubble Space Telescope. Like a peaceful transition from day to night, this new observatory was designed to peer deeper into the cosmic darkness, using infrared vision to penetrate the dust and distance that obscure our view of the early universe. Gently, we discover that Webb's journey began decades ago, in the contemplative minds of astronomers who dreamed of seeing the first light in the universe. The moment when stars began to shine in the cosmic darkness, the telescope's development unfolded like a slow, meditative process, with engineers and scientists working with the patience of cosmic time to create an instrument capable of detecting the faintest whispers of ancient light. As our journey continues into the peaceful realm of Webb's construction, we float through years of careful planning and meticulous engineering. The telescope's primary mirror, composed of 18 hexagonal segments coated in the thinnest layer of gold, was designed to unfold in space like a cosmic flower blooming in the gentle darkness. Each segment was crafted with precision that approaches the sublime, polished to perfection and aligned to work in harmony as a single, magnificent eye looking into the deep. Let's drift into the contemplative understanding of Webb's unique capabilities. Unlike Hubble, which observes primarily invisible light, Webb was designed to see in infrared wavelengths, where the universe reveals different secrets. In this gentle realm of longer wavelengths, the early universe becomes visible as light from the most distant galaxies, stretched by cosmic expansion into the infrared spectrum, where Webb-S instruments can detect and analyze it with unprecedented sensitivity. Now we float toward the remarkable engineering challenge that Webb represented. The telescope needed to operate at temperatures close to absolute zero, colder than the depths of interstellar space, to prevent its own heat from overwhelming the faint infrared signals it was designed to detect. This requirement led to the development of a sunshield the size of a tennis court, composed of 5 layers of material thinner than human hair, each layer working in quiet harmony to block the heat from the Sun, Earth, and Moon. In the quiet space of space itself, Webb found its home at Lagrange Point 2, a gravitationally stable location nearly 1,000,000 miles from Earth, where the gravitational forces of Earth and Sun balance in perfect equilibrium. Here, in this cosmic oasis of stability, the telescope could operate with minimal fuel consumption, gently orbiting this invisible point in space, while maintaining a constant view of the deep universe. The deployment of Webb in space unfolded like a cosmic origami performance, with hundreds of mechanisms working in perfect synchronization to transform the folded telescope into its operational configuration. Gently, we discover that this process required months of careful choreography, with each step monitored and adjusted by mission controllers who understood that a single failure could end humanity's most ambitious space science mission. As our journey continues through Webb's early operations, we witness the gentle process of commissioning, where each instrument was carefully calibrated and tested. The telescope's first images revealed a universe of breathtaking beauty and complexity. But these were merely the beginning of discoveries that would challenge our fundamental understanding of cosmic evolution. Let's drift into the contemplative realization that Webb's true power lies not in individual images, but in its ability to conduct spectroscopic analysis of distant objects. This technique allows astronomers to decode the light from distant galaxies, stars, and planets, revealing their chemical composition, temperature, motion, and other physical properties with unprecedented precision. In the quiet space of scientific observation, Webb began its systematic survey of the deep universe, looking farther back in time than any previous observatory. Each observation was planned with meticulous care, as telescope time on Webb is among the most precious commodities in astronomy, allocated through rigorous peer review to the most promising research projects. Now we float toward understanding the profound implications of Webb's observational strategy. By observing the same regions of sky for extended periods, the telescope could detect objects so faint that their light had been traveling through space for over 13 billion years, showing us the universe as it existed when it was less than 1 billion years old, a mere infant in cosmic terms. Gently, we discover that Webb-S observations would soon reveal a universe far more complex and mature in its early epochs than theoretical models had predicted. The telescope's unprecedented sensitivity and resolution would detect fully formed galaxies at distances so great that they appeared as they were, when the universe was just a few 100 million years old, challenging our understanding of how quickly cosmic structures could form and evolve. As our journey continues into the realm of Webb's first major discoveries, we begin to understand that the telescope wasn't just seeing farther into space, but deeper into time itself, revealing epochs of cosmic history that had never been directly observed before. In the quiet space of these ancient light signals, Webb was about to uncover revelations that would shake the foundations of cosmology and send ripples of excitement and confusion through the astronomical community. The peaceful precision with which Webb operates belies the revolutionary nature of its discoveries. Each observation is conducted with the calm, methodical approach of the universe itself, collecting photons that have traveled across cosmic time to reach us, carrying information about conditions and processes that existed when the universe was fundamentally different from what we observe today. Let's drift into the understanding that Webb's instruments work together in quiet harmony, each specialized for different aspects of astronomical observation. The near-infrared camera captures detailed images of distant objects, while the near-infrared spectrograph breaks their light into component wavelengths, revealing the chemical fingerprints of cosmic phenomena. The mid-infrared instrument peers even deeper into the infrared spectrum, where different cosmic processes become visible, and the fine guidance sensor ensures that the telescope maintains its precise pointing with stability measured in milliseconds. In the quiet space of scientific anticipation, astronomers around the world waited for Webb's first deep-field observations, knowing that these images would reveal the early universe with unprecedented clarity and depth. The telescope's ability to detect objects billions of times fainter than what the human eye can see promised to open new windows into cosmic history, potentially revealing processes and phenomena that had never been observed before. Now we float toward the moment when Webb's first deep observations began to arrive, carrying with them revelations that would challenge decades of theoretical work and force astronomers to reconsider fundamental assumptions about cosmic evolution. In the gentle darkness of space, this technological marvel was about to show us a universe far more surprising than we had ever imagined. In the quiet space of deep time, we must first understand the profound concept that underlies all of Webb's most shocking discoveries. When we look into space, we are simultaneously looking back in time. Like gentle waves on a cosmic ocean, light carries information across the vast distances of the universe. And the farther we peer into space, the further back in time we observe cosmic events. Gently, we discover that this fundamental principle of astronomy transforms Webb into a cosmic time machine, capable of observing the universe as it existed billions of years in the past. The light from distant galaxies that reaches Webb's mirrors began its journey when the universe was young, carrying with it a record of cosmic conditions that existed long before our solar system even formed. As our journey continues into this contemplative realm of cosmic archaeology, we float through the understanding that the most distant objects Webb can observe appear to us as they were when the universe was less than 1 billion years old. In this ancient epoch, the cosmos was a very different place, filled with the first generations of stars and galaxies, undergoing processes of formation and evolution that theoretical models struggled to predict accurately. Let us drift into the peaceful realization that Webb's infrared vision is perfectly suited for this cosmic time travel. As light from distant galaxies travels through the expanding universe, it becomes stretched to longer wavelengths, shifting from visible light into the infrared spectrum where Webb's instruments are most sensitive. This cosmic redshift effect means that the most distant and ancient galaxies become visible only in infrared light, making Webb uniquely qualified to study the early universe. Now we float toward understanding the cosmic distance ladder, the careful series of measurements that allows astronomers to determine how far away distant galaxies lie. By measuring the redshift of galaxy light, astronomers can calculate not only distance but also the age of the universe when that light was emitted, creating a direct observational link to cosmic history. In the quiet space of Webb's first deep observations, astronomers began to notice something unexpected and profound. The galaxies they were detecting at extreme distances appeared far more mature and massive than theoretical models predicted should exist at such early times in cosmic history. These ancient galaxies displayed well-developed spiral structures, massive stellar populations, and signs of complex chemical evolution that should have taken much longer to develop. Gently, we discover that these observations represented the first hints of what would become Webb's most shocking revelation. The early universe was far more active and advanced than anyone had imagined. Galaxies that theory suggested should be small, primitive, and disorganized instead appeared large, mature, and remarkably well-structured, challenging fundamental assumptions about the pace of cosmic evolution. As our journey continues through these early discoveries, we witness the careful process by which astronomers confirmed and reconfirmed their observations. The implications were so significant that extraordinary care was taken to verify that these distant galaxies were indeed as far away and as mature as they appeared to be, ruling out observational errors or misinterpretations of the data. Let us drift into the contemplative understanding of what these mature early galaxies meant for our understanding of cosmic evolution. If galaxies could grow large and complex so quickly after the Big Bang, it suggested that the processes of star formation, galaxy assembly, and cosmic chemical evolution must have proceeded much more rapidly in the early universe than modern conditions would suggest. In the quiet space of scientific revolution, these observations began to challenge the standard model of cosmology itself. The lambda-CDM model, which had successfully explained many aspects of cosmic evolution, seemed inadequate to account for the rapid formation of massive, mature galaxies in the early universe. Astronomers found themselves confronting the possibility that fundamental aspects of their understanding of cosmic evolution might need revision. Now we float toward examining specific examples of these shocking early galaxies. Webb detected galaxies at redshifts corresponding to when the universe was only 400 to 600 million years old. Yet these galaxies contained stellar masses equivalent to billions of suns. In cosmic terms, this was like finding fully grown oak trees in what should have been a nursery of seedlings. Gently, we discover that these early massive galaxies also showed signs of active star formation rates that seemed impossible to sustain. The amount of stellar mass they contained suggested they had been forming stars at rates far exceeding what modern galaxies achieve, raising questions about the availability of gas and dust needed to fuel such intense stellar birth. As our journey continues into the realm of early cosmic chemistry, Webb's spectroscopic observations revealed another shocking aspect of these ancient galaxies. They contained surprisingly high abundances of heavy elements, chemical signatures that indicated multiple generations of stellar evolution had already occurred. In the gentle darkness of the early universe, it appeared that cosmic chemical evolution had progressed much more rapidly than expected. Let's drift into understanding the implications of early chemical enrichment. Heavy elements are produced inside stars and distributed through space. When massive stars explode as supernovae, the presence of significant heavy element abundances in very early galaxies suggested that multiple cycles of star formation and stellar death had already occurred, compressing what should have been billions of years of evolution into a few 100 million years. In the quiet space of these revelations, astronomers began to realize that Webb wasn't just seeing unexpected galaxies. It was revealing a fundamentally different early universe than theoretical models had predicted. The epoch of cosmic dawn appeared to be far more active, complex, and evolved than anyone had imagined possible. Now we float toward examining the morphological complexity of these early galaxies, rather than the simple, irregular structures that models predicted for early cosmic times. Webb observed galaxies with well-developed spiral arms, central bulges, and complex internal structures that indicated sophisticated gravitational organization had already occurred. Gently, we discover that some of these early galaxies appeared to be undergoing major merger events, galactic collisions and interactions that were reshaping their structures and triggering intense bursts of star formation. The frequency and scale of these early mergers suggested that galaxy interaction played a more important role in early cosmic evolution than previously understood. As our journey continues through Webb's observations of the ancient universe, we encounter evidence for early supermassive black holes that challenge our understanding of how these cosmic monsters could have grown so large so quickly. In the centers of some early galaxies, Webb detected active galactic nuclei powered by black holes containing millions or billions of solar masses existing when the universe was less than 1 billion years old. Let's drift into the profound implications of early supermassive black holes. These objects are thought to grow through the accretion of matter over long periods of time, or through mergers with other black holes. The existence of billion solar mass black holes in the early universe suggested that either black hole growth rates were much higher in the past, or that the seeds of these black holes were much more massive than current theories predict. In the quiet space of cosmic contemplation, we begin to understand that Webb's observations were revealing not just individual surprising objects, but a completely different picture of early cosmic evolution. The universe's infancy appeared to be far more eventful, rapid, and complex than the gradual, hierarchical formation process that theoretical models had long predicted. As we prepare to explore the specific mechanisms and processes that might explain these shocking discoveries, we float in the gentle realization that Webb has fundamentally changed our perspective on cosmic history. The telescope's ability to peer into the cosmic deep has revealed a young universe that was already mature, active, and full of surprises that challenge our most fundamental assumptions. about how cosmic structures form and evolve over time. In the quiet space of scientific discovery, Webb's most shocking revelations emerged not as single dramatic observations, but as a pattern of unexpected findings that gradually painted a picture of an early universe far more active and evolved than theoretical models had ever predicted. Gently, we discover that these observations have forced astronomers to confront the possibility that fundamental aspects of cosmological theory may need significant revision. As our journey continues into the realm of early massive galaxies, we encounter Webb's detection of galactic giants existing when the universe was less than 700 million years old. These cosmic behemoths contain stellar masses equivalent to tens of billions of suns, approaching the mass of our own Milky Way galaxy. Yet they exist at a time when the universe was barely 5% of its current age, like finding fully mature ecosystems in what should have been a primordial landscape. These discoveries challenge our understanding of how quickly cosmic structures can form and evolve. Let's drift into the contemplative examination of specific cases that illustrate the magnitude of these revelations. Webb has observed galaxies designated with catalog numbers that seem mundane, but represent revolutionary discoveries. Galaxy JWST 130, for example, appears as it was when the universe was only 325 million years old. Yet it displays a level of structural organization and stellar mass that standard models suggest should have taken several billion years to develop. Now we float toward understanding the challenge these discoveries present to the hierarchical model of galaxy formation. This theoretical framework, which has guided cosmological thinking for decades, suggests that cosmic structures form gradually, with small objects merging to create larger ones over extended periods. Webb's observations of massive, mature galaxies in the early universe suggest that this process occurred far more rapidly than the model predicts, or that additional formation mechanisms were at work. In the quiet space of cosmic irony, we discover that Webb's enhanced sensitivity has revealed not just more distant galaxies, but galaxies that are fundamentally different from what theory predicted should exist at such early times. These ancient galaxies appear to have formed stars at rates far exceeding modern galactic norms, suggesting that the early universe provided conditions for stellar formation that don't exist in today's cosmos. Gently, we discover that the star formation rates observed in these early galaxies often exceed 100 solar masses per year, compared to modern galaxies like the Milky Way that form stars at a rate of only 1 to 2 solar masses per year. This suggests that the early universe contained vast reservoirs of gas and dust available for star formation, and that the physical processes governing stellar birth operated under very different conditions than we observe today. As our journey continues through these revelations, we encounter evidence for early cosmic chemical enrichment that defies conventional understanding. Webb's spectroscopic observations reveal that galaxies existing when the universe was less than a billion years old already contain significant abundances of elements heavier than hydrogen and helium. These heavy elements, forged in the nuclear furnaces of massive stars and distributed through space by stellar explosions, indicate that multiple generations of stellar evolution had already occurred in the cosmic dawn. Let's drift into the implications of early heavy element abundance. The presence of carbon, oxygen, nitrogen, and iron in early galactic spectra suggests that the first generation of stars, composed purely of hydrogen and helium, had already lived out their lives, died in explosive supernovae, and enriched the interstellar medium with the products of nuclear fusion. This cycle of stellar birth, death, and chemical enrichment, which should have taken hundreds of millions of years, appears to have occurred much more rapidly in the early universe. In the quiet space of cosmic chemistry, Webb has revealed that some early galaxies show metallicity levels, measures of heavy element abundance that approach or even exceed those found in modern galaxies. This suggests that the pace of chemical evolution in the early universe was dramatically accelerated compared to current conditions, possibly due to higher star formation rates, different stellar mass distributions, or more efficient mixing of stellar products throughout early galactic environments. Now we float toward examining the morphological sophistication of early galaxies, revealed by Webb's high-resolution imaging, rather than the simple, irregular structures predicted by theory. Many early galaxies display complex morphologies including well-developed spiral arms, central bulges, and organized disk structures. These features indicate that gravitational processes had already sculpted these galaxies into sophisticated forms, suggesting that galactic dynamics operated more efficiently in the early universe than current models predict. Gently, we discover that Webb has observed early galaxies undergoing active merger processes, galactic collisions and interactions that are reshaping their structures and triggering intense episodes of star formation. The frequency of these merger events in the early universe appears much higher than in the modern cosmos, suggesting that galaxy interaction played a crucial role in rapid early galactic evolution. As our journey continues into the realm of early supermassive black holes, we encounter some of Webb's most shocking discoveries. The telescope has detected active galactic nuclei powered by supermassive black holes in galaxies existing when the universe was less than 800 million years old. These black holes contain masses equivalent to hundreds of millions or even billions of suns, representing gravitational monsters that shouldn't have had time to grow so large so quickly. Let's drift into the puzzle of early black hole formation and growth. Supermassive black holes are thought to grow through two primary mechanisms: the accretion of surrounding matter and mergers with other black holes. Both processes are limited by physical constraints that should prevent rapid growth. To billion solar mass scales in the early universe, the existence of such massive black holes at early cosmic times suggests either that black hole formation and growth mechanisms operated differently in the past, or that the initial seeds of these black holes were much more massive than current theories predict. In the quiet space of theoretical challenge, these early supermassive black holes present what astronomers call the early quasar problem. The standard model suggests that black holes begin as stellar remnants, with masses of tens of solar masses, then grow through accretion and mergers over billions of years. However, even under optimal conditions, it appears impossible for stellar mass black holes to grow to billion solar mass scales. In the time available in the early universe, now we float toward exploring potential solutions to the early black hole puzzle. Some theoretical models propose that the first black holes formed not from stellar collapse, but from the direct gravitational collapse of primordial gas clouds, creating intermediate mass black holes with masses of thousands or tens of thousands of solar masses. These larger seeds could potentially grow to supermassive scales more quickly than stellar mass seeds, but this process remains highly speculative and difficult to observe directly. Gently, we discover that Webb's observations have also revealed unexpected correlations between early galaxy properties and their supermassive black holes. In the modern universe, there are well-established relationships between black hole mass and the properties of their host galaxies, but early systems appear to deviate from these relationships, suggesting that black hole galaxy coevolution proceeded differently in the cosmic past. As our journey continues through Webb's revelations about early cosmic structure, we encounter evidence for large-scale organization that formed much earlier than expected. The telescope has observed protogalaxy clusters, collections of galaxies in the process of gravitational assembly, at distances corresponding to when the universe was less than 1 billion years old. These structures indicate that cosmic large-scale structure formation began very early in cosmic history. Let's drift into understanding the implications of early large-scale structure formation. Galaxy clusters are among the most massive gravitationally bound objects in the universe, requiring significant time to assemble through the gravitational attraction of dark matter and normal matter. The observation of cluster formation at such early times suggests that the universe's initial density fluctuations may have been larger than current models predict, or that structure formation processes operated more efficiently in the past. In the quiet space of cosmic architecture, Webb has revealed that the early universe already showed signs of the cosmic web, the large-scale network of dark matter filaments that connects galaxies and galaxy clusters across cosmic distances. The presence of organized large-scale structure at such early times indicates that the fundamental architecture of the universe was established much sooner than theoretical models suggested. Now we float toward examining the broader implications of these shocking discoveries. Webb's observations suggest that the early universe was a far more active and rapidly evolving place than previously imagined, with star formation, galaxy assembly, black hole growth, and large-scale structure formation all proceeding at accelerated rates compared to modern conditions. As we prepare to explore the atmospheric discoveries and exoplanet revelations that Webb has provided, we rest in the gentle realization that these cosmological surprises represent just one aspect of the telescope's revolutionary impact on astronomy. The same technological capabilities that revealed the unexpected complexity of the early universe have also opened new windows into the atmospheres of distant worlds, potentially revealing conditions suitable for life in ways that continue to surprise and delight the astronomical community. In the quiet space of planetary science, Webb's sophisticated instruments have turned their attention from the distant cosmos to the atmospheric mysteries of worlds orbiting other stars, revealing compositions and conditions that continue to surprise astronomers with their diversity and complexity. Gently, we discover that the same technological capabilities that unveiled shocking truths about early galaxies have also revolutionized our understanding of exoplanetary atmospheres, opening windows into alien worlds that challenge our assumptions about planetary formation and evolution. As our journey continues into the realm of atmospheric analysis, we float through Webb's unprecedented ability to conduct transmission spectroscopy of exoplanets. When a planet passes in front of its host star as viewed from Earth, starlight filters through the planet's atmosphere, creating spectroscopic signatures that reveal the chemical composition, temperature, structure, and physical properties of atmospheric layers with extraordinary precision. Let us drift into the contemplative understanding of how Webb's infrared capabilities make it uniquely suited for atmospheric studies. Many molecular signatures of atmospheric components, including water vapor, carbon dioxide, methane, and various organic compounds, produce their strongest spectral features in the infrared wavelengths where Webb operates. This allows the telescope to detect and analyze atmospheric compositions with sensitivity far exceeding any previous space-based observatory. Now we float toward examining Webb's discovery of water vapor in the atmospheres of distant worlds, a finding that has profound implications for our understanding of planetary formation and the potential for habitability. The telescope has detected water signatures in the atmospheres of hot gas giants, warm sub-Neptunes, and even some rocky planets, revealing that water is far more common in exoplanetary systems than early observations suggested. In the quiet space of chemical revelation, Webb has discovered atmospheric compositions that challenge traditional models of planetary formation. Some exoplanets show evidence for atmospheric metallicity, the abundance of elements heavier than hydrogen and helium that differs significantly from their host stars. This suggests that planetary atmospheres can be enriched or depleted in heavy elements through processes not fully understood, indicating that planetary formation involves more complex chemical evolution than simple models predict. Gently, we discover that Webb has revealed the presence of clouds and hazes in exoplanetary atmospheres with unprecedented detail. These atmospheric features, composed of various condensed materials including silicates, sulfides, and organic compounds, play crucial roles in determining planetary temperature, atmospheric dynamics, and potential habitability. The diversity of cloud compositions observed by Webb suggests that atmospheric chemistry varies dramatically across different types of exoplanets. As our journey continues through Webb's atmospheric discoveries, we encounter evidence for atmospheric dynamics that reveal the complex weather patterns of distant worlds. The telescope has detected signs of atmospheric circulation, temperature variations between day and night sides of tidally locked planets, and evidence for dynamic atmospheric processes that transport heat and chemicals across planetary atmospheres. Let's drift into the fascinating realm of hot Jupiter atmospheres, where Webb has made some of its most detailed atmospheric characterizations. These massive planets, orbiting very close to their host stars, experience extreme temperatures and intense stellar radiation that drive exotic atmospheric chemistry. Webb has detected evidence for thermal inversions, atmospheric layers where temperature increases with altitude, caused by the absorption of stellar radiation by atmospheric molecules, like titanium oxide and vanadium oxide, in the quiet space of atmospheric diversity. Webb has revealed that no two exoplanetary atmospheres are exactly alike. Each world shows a unique combination of chemical compositions, temperature structures, and dynamic processes that reflect the specific conditions of planetary formation and evolution. This diversity suggests that planetary systems form through a complex interplay of factors, including stellar properties, disk composition, migration processes, and long-term evolutionary changes. Now we float toward Webb's discoveries of organic compounds in exoplanetary atmospheres, findings that have profound implications for astrobiology and the search for life beyond Earth. The telescope has detected carbon-bearing molecules including carbon monoxide, carbon dioxide, and methane in various exoplanetary atmospheres, along with evidence for more complex organic chemistry that could potentially support biological processes. Gently, we discover that Webb's detection of methane in exoplanetary atmospheres presents both exciting possibilities and complex interpretive challenges. While methane can be produced by biological processes, it can also be generated through various non-biological mechanisms including atmospheric chemistry, geological processes, and interactions with stellar radiation, distinguishing between biological and non-biological sources of atmospheric methane requires careful analysis of additional atmospheric components and detailed understanding of planetary conditions. As our journey continues into the realm of potentially habitable worlds, Webb has begun characterizing the atmospheres of rocky planets orbiting in the habitable zones of their host stars, the regions where liquid water could potentially exist on planetary surfaces. These observations represent some of the most technically challenging atmospheric studies ever attempted, requiring extraordinary precision to detect the subtle spectroscopic signatures of thin atmospheres around small planets. Let's drift into understanding the challenges of characterizing potentially habitable exoplanets. Rocky planets produce much smaller atmospheric signals than gas giants, requiring longer observation times and more sophisticated analysis techniques to extract meaningful information about atmospheric composition. Webb's success in detecting atmospheric signatures from rocky exoplanets represents a major technological achievement that opens new possibilities for finding signs of habitability or even life itself. In the quiet space of habitability assessment, Webb has revealed that the presence of atmospheres around rocky exoplanets is not guaranteed. Some rocky planets, particularly those orbiting very close to active stars, may have lost their atmospheres to stellar radiation and stellar winds. Webb's ability to detect or rule out atmospheric retention around rocky exoplanets provides crucial information about which worlds might maintain conditions suitable for liquid water and potentially life. Now we float toward examining Webb's discoveries about atmospheric escape processes, mechanisms by which planetary atmospheres can be stripped away by stellar radiation and stellar winds. The telescope has observed evidence for atmospheric loss in various exoplanetary systems, revealing that atmospheric retention depends on complex interactions between planetary mass, stellar activity, magnetic field strength, and atmospheric composition. Gently, we discover that Webb has detected signatures of atmospheric escape in the form of extended hydrogen and envelopes around some exoplanets, revealing that these worlds are actively losing atmospheric material to space. These observations provide direct evidence for ongoing atmospheric evolution and help astronomers understand which types of planets can retain their atmospheres over cosmic time scales. As our journey continues through Webb's atmospheric revelations, we encounter evidence for atmospheric chemistry that operates under extreme conditions never experienced on Earth. Some exoplanets show evidence for atmospheric temperatures exceeding 2000 Kelvin, conditions where even rocky materials can exist as vapor, creating exotic atmospheric compositions that challenge our understanding of planetary physics and chemistry. Let's drift into the realm of atmospheric thermal structure, where Webb has revealed complex temperature profiles that result from the interplay between stellar heating, atmospheric composition, and dynamic processes. The telescope has detected evidence for thermal inversions, atmospheric layers with unusual temperature gradients, and thermal phase variations that reveal how heat is transported and redistributed in exoplanetary atmospheres in the quiet space of comparative planetology. Webb's atmospheric studies have revealed that exoplanetary atmospheres span a far greater range of compositions and conditions than the planets in our own solar system. This diversity provides valuable insights into the range of planetary environments that can exist, expanding our understanding of planetary formation processes and the potential for habitable conditions in the universe. Now we float toward understanding how Webb's atmospheric discoveries inform our search for potentially habitable worlds and signs of life. The telescope's ability to detect water vapor, assess atmospheric retention, and characterize chemical compositions provides crucial information for identifying worlds that might support liquid water and the complex chemistry necessary for life as we know it. As we prepare to explore Webb's revelations about cosmic architecture and large-scale structure, we rest in the gentle appreciation of how the telescope has transformed our understanding of exoplanetary atmospheres. These discoveries reveal a universe filled with worlds of extraordinary diversity, each shaped by unique combinations of physical and chemical processes that create atmospheric environments ranging from familiar to utterly alien, expanding our perspective on the potential for habitable conditions throughout the cosmos. In the quiet space of cosmic contemplation, we now turn our attention to Webb's revelations about the large-scale architecture of the universe, discoveries that have illuminated how matter organizes itself across the vastest scales of space and time. Gently, we discover that the same unprecedented observational capabilities that revealed shocking truths about early galaxies and exoplanetary atmospheres have also provided new insights into the cosmic web, the fundamental scaffolding upon which all cosmic structure is built. As our journey continues into the realm of large-scale structure formation, we float through Webb's observations of how galaxies, galaxy clusters, and dark matter organize themselves into the complex network of filaments, nodes, and voids that characterize the mature universe. These observations reveal that the cosmic Webb's basic architecture was established much earlier in cosmic history than previous studies had suggested, indicating that the universe's organizational principles operated with remarkable efficiency in its youth. Let's drift into the contemplative understanding of dark matter's role in cosmic architecture, revealed through Webb's observations of gravitational lensing effects. When light from distant galaxies passes through regions of concentrated dark matter, its path becomes curved by gravitational forces, creating distorted images that allow astronomers to map the distribution of this invisible component of cosmic structure. Webb's high-resolution observations have provided unprecedented detail about dark matter's large-scale distribution and its role in shaping cosmic evolution. Now we float toward examining Webb's discoveries about early galaxy cluster formation, revealing that these massive gravitational structures began assembling much sooner than theoretical models predicted. The telescope has observed protoclusters, collections of galaxies, in the process of gravitational assembly at distances corresponding to when the universe was less than 2 billion years old, indicating that large-scale structure formation proceeded more rapidly in the early universe than current simulations suggest. In the quiet space of gravitational architecture, Webb has revealed how galaxy clusters influence the formation and evolution of their constituent galaxies through environmental effects that operate across cosmic scales. The telescope has observed evidence for increased star formation rates in cluster galaxies during early cosmic epochs, suggesting that the dense environment of forming clusters provided conditions that enhanced galactic evolution through gravitational interactions and increased gas density. Gently, we discover that Webb's observations of galaxy cluster evolution reveal a complex interplay between dark matter dynamics, gas physics, and stellar formation processes that shape cluster properties over cosmic time. The telescope has detected evidence for active galactic nuclei in cluster centers, supermassive black holes that regulate star formation, and gas cooling through feedback mechanisms that operate across cluster-wide scales. As our journey continues through the realm of cosmic filaments, we encounter Webb's observations of the thread-like structures that connect galaxy clusters. Across hundreds of millions of light-years, these cosmic filaments, composed primarily of dark matter with embedded streams of ordinary matter, serve as highways along which galaxies and galaxy groups migrate, creating the interconnected network that characterizes large-scale cosmic structure. Let us drift into understanding how Webb's infrared capabilities have revealed previously hidden aspects of cosmic filament structure. The telescope has detected warm gas and dust associated with cosmic filaments, material that connects distant galaxies and provides fuel for ongoing star formation. These observations reveal that cosmic filaments are not empty conduits but active environments, where galaxy formation and evolution continue to occur over cosmic time. In the quiet space of cosmic voids, Webb has provided new insights into the largest empty regions of the universe, vast spaces that contain few galaxies but play crucial roles in cosmic structure formation. The telescope's sensitive observations have revealed that cosmic voids are not completely empty, but contain sparse populations of small galaxies and traces of gas that provide information about conditions in the least dense regions of the universe. Now we float toward examining Webb's contributions to understanding cosmic structure on the largest observable scales, revealing patterns in galaxy distribution that reflect the initial conditions of the universe and the subsequent evolution of cosmic density fluctuations. These observations provide direct tests of cosmological models and help astronomers understand how the universe's current large-scale structure emerged from its initial nearly uniform state. Gently, we discover that Webb has observed evidence for cosmic structure formation that challenges aspects of the standard cosmological model. The telescope has detected large-scale structures in galaxy distributions that appear more organized and mature at early cosmic times than simulations based on current dark matter models predict, suggesting that either initial conditions were different from current assumptions, or that structure formation processes operated more efficiently in the past. As our journey continues into the realm of dark matter physics, Webb's gravitational lensing observations have provided new constraints on the properties of this mysterious cosmic component. The telescope has observed how dark matter clumps and filaments bend light from background galaxies, revealing that dark matter exhibits the gravitational properties expected from theoretical models, while remaining invisible to direct electromagnetic observation. Let's drift into the contemplative examination of how Webb's observations inform our understanding of dark energy, the mysterious force driving cosmic expansion acceleration. While Webb cannot directly observe dark energy, its measurements of cosmic structure growth and galaxy evolution provide indirect constraints on dark energy properties by revealing how structure formation has proceeded over cosmic time under the influence of accelerating expansion. In the quiet space of cosmic evolution, Webb has revealed how the balance between dark matter, dark energy, and ordinary matter has shaped cosmic structure formation across different epochs. The telescope's observations show that early cosmic times were dominated by matter density, promoting rapid structure formation, while later epochs have been increasingly influenced by dark energy, which tends to inhibit further structure growth. Now we float toward understanding how Webb's structural observations connect to its discoveries about early galaxy formation and black hole growth. The telescope has revealed that early massive galaxies and supermassive black holes formed within the context of rapidly assembling dark matter structures, suggesting that efficient structure formation in the early universe provided the gravitational environment necessary for accelerated galaxy and black hole evolution. Gently, we discover that Webb's observations of cosmic structure span scales from individual galaxies to the largest observable structures in the universe, providing a comprehensive view of how matter organizes itself across the cosmic hierarchy. These observations reveal that structure formation processes operate coherently across vastly different scales, with small-scale processes influencing large-scale structure and vice versa. As our journey continues through Webb's revelations about cosmic magnetic fields, we encounter evidence for large-scale magnetic structures that influence galaxy formation, star formation, and cosmic ray propagation across cosmic scales. The telescope has detected polarized emission from dust grains aligned by magnetic fields, revealing that cosmic magnetism plays important roles in structure formation and galactic evolution. Let's drift into understanding how Webb's structural observations contribute to our knowledge of cosmic reionization, the epoch when the first stars and galaxies ionized the hydrogen gas that filled the early universe. The telescope has observed evidence for ionized regions around early galaxies, revealing how these first light sources gradually transformed the universe from a neutral, opaque state to the ionized, transparent condition we observe today. In the quiet space of cosmic feedback processes, Webb has revealed how stellar formation, stellar explosions, and active galactic nuclei influence structure formation across cosmic scales. The telescope has observed evidence for galactic winds, outflows driven by stellar feedback and black hole activity, that redistribute gas and metals across large-scale structures, influencing subsequent generations of galaxy formation. Now we float toward examining how Webb's structural observations provide new insights into cosmic inflation, the theoretical process that drove rapid expansion in the universe's earliest moments. While Webb cannot directly observe inflationary processes, its measurements of large-scale structure patterns provide tests of inflationary predictions about the initial density fluctuations that seeded all subsequent structure formation. As we prepare to explore the broader implications of Webb's discoveries for our understanding of cosmic evolution and cosmological theory, we rest in the gentle appreciation of how the telescope has revealed the universe as a coherently structured entity where processes operating across vastly different scales influence each other through gravitational, electromagnetic, and thermodynamic interactions that span the entire observable cosmos. In the quiet space of scientific reflection, we now contemplate how Webb's shocking discoveries have fundamentally altered our understanding of cosmic evolution, challenging long-held assumptions about the pace and mechanisms of structure formation while opening new avenues of inquiry that will guide astronomical research for decades to come. Gently, we discover that these revelations represent not just incremental advances in knowledge, but paradigm shifts that require us to reconsider basic principles of cosmological theory. As our journey continues into the realm of theoretical implications, we float through the recognition that Webb's observations of mature early galaxies have challenged the hierarchical model of structure formation that has dominated cosmological thinking for decades. This model, which suggests that cosmic structures form gradually through the merger of smaller components, appears inadequate to explain the rapid formation of massive complex galaxies observed in the early universe, suggesting that additional formation mechanisms or different initial conditions may be necessary. Let's drift into the contemplative examination of how these discoveries impact our understanding of dark matter physics. Webb's observations of early massive structures require that dark matter began clumping into large-scale structures much earlier and more efficiently than current simulations predict. This suggests either that dark matter has properties not accounted for in current models, or that the initial distribution of dark matter density fluctuations was different from what cosmological models assume. Now we float toward understanding the implications for cosmic star formation history. Webb's detection of intense star formation rates in early galaxies suggests that the universe went through a period of extraordinarily active stellar birth that doesn't appear in current models of cosmic evolution. This early burst of star formation may have fundamentally altered the chemical evolution of the universe, enriching the intergalactic medium with heavy elements much sooner than previously expected. In the quiet space of cosmological parameters, Webb's discoveries have implications for fundamental constants that describe our universe's properties and evolution. The rapid formation of early structures may require adjustments to parameters describing dark matter density, the amplitude of initial density fluctuations, or the efficiency of star formation processes in the early universe. These adjustments could cascade through cosmological models, affecting predictions about everything from the cosmic microwave background to the ultimate fate of the universe. Gently, we discover that Webb's observations of early supermassive black holes challenge our understanding of how these cosmic giants form and grow. the existence of billion solar-mass black holes when the universe was less than 1 billion years old suggests that either black hole formation mechanisms operated very differently in the past, or that the seeds of supermassive black holes were much more massive than current theories predict. This black hole formation puzzle may require entirely new theoretical frameworks to resolve. As our journey continues through the implications for galaxy formation theory, we encounter the possibility that early galaxies formed through processes that don't operate efficiently in the modern universe. The conditions present in the early cosmos, including higher gas densities, different radiation fields, and more active merger environments, may have enabled galaxy formation mechanisms that we don't observe today, making early cosmic evolution fundamentally different from modern galactic processes. Let's drift into understanding how Webb's atmospheric discoveries impact our search for life beyond Earth. The telescope's detection of diverse atmospheric compositions around exoplanets reveals that potentially habitable conditions may be more common and varied than previously expected. However, Webb has also shown that atmospheric retention is challenging around many types of planets, particularly those orbiting active stars, providing important constraints on where life might be able to survive over cosmic time scales. In the quiet space of astrobiology implications, Webb's ability to detect atmospheric compositions with unprecedented precision opens new possibilities for identifying biosignatures, atmospheric gases that could indicate the presence of life. However, the telescope has also revealed that distinguishing between biological and non-biological sources of potential biosignature gases requires detailed understanding of planetary atmospheric chemistry and evolution, making the search for life more complex but also more scientifically rigorous. Now we float toward examining how Webb's discoveries influence future space mission planning. The telescope's revelations about early cosmic evolution, exoplanetary diversity, and large-scale structure formation provide crucial guidance for designing future observatories and space missions. Understanding what Webb has revealed helps astronomers identify the most important scientific questions for future investigation and the technological capabilities needed to address them. Gently, we discover that Webb's success in detecting unexpected phenomena demonstrates the importance of building space telescopes with capabilities that exceed current theoretical predictions. The telescope's most shocking discoveries were not predicted by models, suggesting that future observatories must be designed with sufficient sensitivity and flexibility to detect phenomena that current theory doesn't anticipate. As our journey continues into the realm of technological implications, we encounter recognition that Webb's discoveries validate the importance of infrared astronomy. For understanding cosmic evolution, the telescope's infrared capabilities have been crucial for detecting redshifted light from early galaxies, analyzing exoplanetary atmospheres, and mapping large-scale structure formation, demonstrating that future space observatories must continue advancing infrared technology to push the boundaries of cosmic observation. Let's drift into understanding how Webb's discoveries inform ground-based astronomy. The telescope's revelations about early galaxies, exoplanetary atmospheres, and cosmic structure provide targets and phenomena for detailed follow-up observations with ground-based telescopes. Webb's discoveries create scientific synergies, where space-based detection enables ground-based characterization, maximizing the scientific return from both space and ground-based observational facilities. In the quiet space of educational implications, Webb's shocking discoveries provide powerful tools for communicating the excitement and importance of scientific research to the public. The telescope's ability to reveal unexpected cosmic phenomena demonstrates how scientific observation can overturn established theories and reveal new aspects of natural reality, inspiring future generations of scientists and maintaining public support for space exploration and scientific research. Now we float toward examining how Webb's discoveries impact our philosophical understanding of humanity's place in the universe. The telescope's revelations about cosmic diversity, from early galactic complexity to exoplanetary atmospheric variety, suggest that the universe is far more active, complex, and potentially habitable than previous observations indicated. These discoveries expand our perspective on cosmic evolution and the potential prevalence of conditions suitable for life. Gently, we discover that Webb-S observations raise profound questions about the nature of cosmic fine-tuning and the conditions necessary for complexity to emerge in the universe. The rapid formation of early structures and the diversity of exoplanetary environments suggest that the universe may be more conducive to complex structure formation than previously expected, potentially influencing philosophical discussions about cosmic evolution and the emergence of complexity. As our journey continues through the implications for theoretical physics, we encounter recognition that Webb-S discoveries may require extensions or modifications to our current understanding of fundamental physics. The telescope's observations of early cosmic evolution challenge aspects of the standard model of cosmology, potentially requiring new physics beyond the current paradigm of dark matter and dark energy to fully explain observed phenomena. Let us drift into understanding how Webb-S discoveries will influence the next generation of cosmological simulations and theoretical models. The telescope's observations provide new constraints and benchmarks that theoretical models must reproduce, requiring more sophisticated simulations that can account for the rapid pace of early cosmic evolution and the diversity of cosmic environments that Webb has revealed. In the quiet space of future exploration, we contemplate how Webb's discoveries set the stage for even more ambitious future missions. The telescope's success in revealing unexpected cosmic phenomena demonstrates the scientific value of pushing observational capabilities to new limits, providing justification for future space telescopes with even greater sensitivity, resolution, and wavelength coverage. As we prepare for our final contemplation of Webb's revolutionary impact on astronomy, we rest in the gentle recognition that the telescope's most important contribution may be its demonstration that the universe remains full of surprises, capable of challenging our best theoretical understanding and revealing new phenomena that expand our appreciation for the complexity and beauty of cosmic evolution. In the quiet space of cosmic reflection, as our journey through Webb's revolutionary discoveries draws to a peaceful close, we find ourselves fundamentally changed by the revelations this remarkable telescope has provided. Like gentle waves that reshape distant shores, Webb's observations have gradually but profoundly altered our understanding of cosmic evolution, revealing a universe far more complex, active, and surprising than our theoretical models had ever predicted. Gently, we discover that Webb's most profound contribution lies not in any single discovery, but in its demonstration that the cosmos remains capable of shocking us, challenging our assumptions, and revealing new layers of complexity that expand our appreciation for the intricate beauty of cosmic evolution. The telescope has shown us that the universe's early epochs were far more eventful than we imagined, filled with rapidly forming galaxies, quickly growing black holes, and efficient structure formation processes that compressed billions of years of expected evolution into cosmic youth. As our journey continues through this final contemplation, we float in the recognition that Webb has revolutionized multiple fields of astronomy simultaneously, from cosmology to exoplanetary science, from stellar formation to large-scale structure evolution. The telescope's unprecedented capabilities have opened new windows of observation that reveal phenomena we didn't know existed and challenge theories we thought were well established. Let us drift into understanding that Webb's atmospheric discoveries have transformed our approach to searching for life beyond Earth. The telescope's ability to characterize exoplanetary atmospheres with extraordinary precision has revealed both the promise and complexity of identifying potentially habitable worlds. We now know that atmospheric diversity exceeds our expectations, that atmospheric retention presents significant challenges for many worlds, and that distinguishing between biological and non-biological atmospheric signatures requires sophisticated analysis that pushes the boundaries of our interpretive capabilities. Now we float toward appreciating how Webb's cosmic time machine capabilities have revealed that looking deeper into space truly means looking further back in time, showing us epochs of cosmic history that were previously beyond observational reach. These ancient light signals carry information about cosmic conditions that existed when the universe was fundamentally different, providing direct observational access to cosmic evolution that complements and challenges theoretical understanding. In the quiet space of scientific methodology, Webb's discoveries demonstrate the crucial importance of building observational capabilities that exceed current theoretical predictions. The telescope's most shocking revelations were not anticipated by existing models, showing that nature's creativity surpasses our theoretical imagination and that future space missions must be designed with the flexibility and sensitivity to detect phenomena we haven't yet conceived. Gently, we discover that Webb's success validates the patient, methodical approach of space-based astronomy, where years of careful engineering and decades of technological development create instruments capable of transforming human understanding. The telescope represents the culmination of collective human ingenuity, international cooperation, and sustained commitment to exploring the cosmos with ever greater precision and sensitivity. As our journey continues into appreciation of Webb's technological achievement, we recognize that the telescope's success enables and inspires future generations of space observatories. Webb's discoveries provide scientific justification for even more ambitious future missions, while demonstrating the observational techniques and analytical methods that will guide cosmic exploration for decades to come. Let's drift into understanding how Webb's revelations connect us to the broader narrative of cosmic evolution. The telescope has shown us that we exist within a universe of extraordinary dynamism and creativity, where structure formation processes operate across vast scales of space and time to create the complex cosmic architecture we observe today. From the smallest exoplanetary atmospheres to the largest galaxy clusters, Webb reveals a cosmos characterized by intricate relationships and feedback processes that shape evolution across all scales. In the quiet space of cosmic perspective, Webb's discoveries remind us that human civilization exists within this vast, evolving cosmic context. The heavy elements in our bodies were forged in stellar cores billions of years ago. The gravitational environment that enabled our solar system's formation was shaped by cosmic structure evolution, spanning cosmic history, and the potential for life that we represent may be shared by worlds throughout the galaxy whose atmospheres Webb is beginning to characterize. Now we float toward recognizing that Webb's revolutionary impact extends beyond scientific discovery to cultural and philosophical implications. The telescope's revelations about cosmic complexity and exoplanetary diversity expand our perspective on humanity's place in the universe, suggesting that we exist within a cosmos far more active and potentially life-bearing than previous observations indicated. Gently, we discover that Webb's ongoing mission promises continued revelations that will further challenge and refine our understanding of cosmic evolution. The telescope's operational lifetime will span many years, providing opportunities for follow-up observations, deeper surveys, and investigations of phenomena that current discoveries have only begun to reveal. Each new observation cycle brings the potential for additional surprises that could further revolutionize astronomical understanding. As our gentle journey through Webb's cosmic revelations reaches its peaceful conclusion, we rest in the profound appreciation that this remarkable telescope has demonstrated the universe's capacity to surprise, challenge, and inspire us. Webb's discoveries remind us that scientific exploration remains one of humanity's most profound endeavors, capable of revealing new aspects of cosmic reality that expand our understanding and deepen our appreciation for the extraordinary universe we inhabit. In the quiet space of cosmic wonder, we recognize that Webb's legacy will extend far beyond its operational lifetime. The telescope's discoveries will influence astronomical research for generations. Its technological innovations will guide future space mission development, and its revelations about cosmic evolution will reshape how we understand our place within the vast, evolving cosmos. Let's drift into final appreciation that Webb's journey of discovery continues, with each new observation potentially revealing additional cosmic surprises that challenge our understanding and expand our perspective. The telescope maintains its patient vigil in the cosmic deep, collecting ancient photons that carry information about cosmic processes we're still learning to interpret and understand. As we float in peaceful contemplation of all that Webb has revealed, and all that remains to be discovered, we understand that the telescope's most profound gift may be its demonstration that the universe remains fundamentally mysterious, capable of surprising us with revelations that exceed our theoretical expectations and challenge us to expand our understanding of cosmic evolution, structure formation, and the potential for life throughout the cosmos. In the gentle darkness of space where Webb continues its revolutionary observations, we find comfort in knowing that human curiosity and ingenuity have created an instrument capable of revealing cosmic truths that expand our perspective and deepen our appreciation for the extraordinary universe we call home. The telescope's discoveries remind us that we are participants in cosmic evolution, connected through physics and chemistry to processes that span the observable universe and cosmic history. Now, as our cosmic meditation draws to its peaceful close, we carry with us the profound recognition that Webb has fundamentally altered our understanding of cosmic evolution while demonstrating that the universe retains its capacity to surprise and inspire us with revelations that challenge our assumptions and expand our appreciation for the complexity and beauty of cosmic existence. Good night from the sleepy scientist.